Hi, good afternoon, good morning, based on the timing where you're watching this video. I'm Adam Erkenbrack. This presentation is part of the Machine Learning 2 class for Southern Methodist University. Today, I'm going to be talking a little bit about Agentic RAG. So the agenda for this presentation is first going to cover a discussion of what chat LLMs are, just a brief introduction so that you can understand how it plays into RAG. Then I'll talk about RAG, how does RAG work? Then I'm going to talk about the agentic aspect of RAG, which is how we create the agents and what agents are exactly and how they do tasks and how they can simplify your work. And then I'll do an actual walkthrough of some of the code that I tested and wrote up for this presentation. So let's talk a little bit about what RAG is. RAG is a system that is designed to enhance an LLM so that it can deal with more recent developments that extend beyond its original training data. It helps reduce hallucinations. It improves the accuracy of response in a chat. It makes sure that information is relevant because it's actually new. And it actually helps the LLM learn because you're adding new information to its database. So if we were to talk about how RAG works, so a normal LLM, basically what happens is you have a body of original content that is put into this massive database. And in the case of most LLMs, you're talking about billions of documents or videos or audio that all go into this database. And then the LLM is trained using neural networks on that particular data. And then that LLM, which is a large language model, is able to take that information and provide a human readable and understandable response through an algorithm, a chat algorithm that provides a response to that query. So that's how normal models are trained. So if you were to take the case of Meta's most recent large language model, which is Llama 3.2, it was trained with data that goes up till December of 2023, but none of its responses would cover any data after that cutoff date. It would be limited to that type of response. So how Retrieval Augmented Generation, RAG, works is you've got the original thing that we talked about with the LLM being conducted, but basically users are looking for particular information, and they might use an all search source to add relevant new information or new content to the existing data that the LLM has. So that could be a local database, for instance, if a company had a bunch of data that it held, or it had PDFs, documents in store, or if it wanted to scrape the internet to get all relevant information related to a topic. That would be stuff that is new content that was not included in the pre-training of that LLM. And that new content will then be sent into a vector storage database and the content embedded. We'll talk about that in more detail at a later point. But a smart retriever is then used, which conducts a semantic search on that new database or that new content so that the chatbot can provide a more recent answer. And that's kind of how the retrieval augmented generation takes place. The retrieval is the retrieval of new information that augments the generation of a natural language response to the user. And that's kind of how RAG works. But it's a very good way of improving responses from these bots. Now, let's go through the steps of RAG, and we're going to talk about the preparing of new data first. So let's say you have your unstructured sources. These could be from all the things that we listed before. That unstructured data is extracted and put into documents, and then the documents are chunked into little pieces, or the documents are broken up so that they're easier for the computer to read and embed, and metadata is preserved. And then they store that data and put all of that information into a vector database. So let's walk through the steps of that. First, let's talk about the chunking process. So let's say you have an external document. All NLP, natural language processing, uses a system that tokenizes documents. And a token is basically a word or punctuation or anything within that document. And each word is called a token. And then you can use various tools to transform that data. And in the case of this particular presentation, I used Langchain, which is has multiple text splitters and different types of text splitters, and you can decide on your chunking strategy. So a token can be chunked based on the characters in that token, or it can be recursively chunked so that it covers a specific amount or number of characters that has some degree of overlap. Or you could pull out just the chunks in paragraphs, or you could pull out the chunks with semantic meaning. That means every 1, 2, 3 sentences are pulled out as a group, so you get the full context of the semantic meaning behind those texts as each sentence is related to the other sentence. And so if you're talking about how those sentences are related to each other, the semantic splitter would capture every element of that. And then the chunks are broken up into little, what they're called documents, but they're still chunks. They're chunk documents. And let's say one of those documents has some text. This is some text. So one sentence in that particular chunk. Those chunks are broken up, are given vectors based on their relations to other words and how closely associated those other words are. We'll talk about that in detail in just a minute. And then those high dimensional vectors are put into embeddings in a lower dimension. And these embeddings can include words, but they can also include sentences and how those sentences are associated with each one. And each word gets a semantic embedding. So for the case of our system that we will be previewing, we're using Langchain again, and we're using Chroma as our database, our vector database. Chroma is just a free application that's available online. And you can just see here, we're also using recursive character text splitting to do the actual splits, and the chunk sizes are limited to a certain size, and you can adjust these based on your needs. We secure the metadata, giving an example of the metadata that should be pulled for. In this case, this is a tool, but I'll talk about that when I get to the agents. And then splitting using a splitter to break up those little chunks into smaller pieces. And this last piece of text is just for verification purposes, so I can make sure how it's breaking up each of the texts. So once the text is chunked, you have to embed the data. And so how embedding works is basically you have the words broken up into tokens, and each token has a numerical position that it is given. And that numerical position is based on how it relates to other words. So for instance, if two words are closely or are far apart in distance on the spectrum on a 2D grid, you would find that their distance would be greater than 90 degrees. But if they're more similar, then that distance would be less than 90 degrees. So in the case here, we have king and queen. They are similar words because they're different titles. And man and woman are genders, but those titles are associated with the gender of a man and woman. So they're all within a close, similar grid section. And once you have those vectors that have defined the semantic relationships, you have the embedding. So take that to another level. If you were to add multiple dimensions, so in this case we have 3 dimensions, but you're looking at words in 3-dimensional state, but those dimensions could expand to any level. So you could look at what we would call traits, and these would be like, is man a living being? Is man a feline? So you might have a category that's called feline. A human, the gender type, royalty. You could break it up based on parts of speech, verb. Is it a plural word or singular? And so if you look at this case, man, this case runs from 1 to -1. So man is a living being, so it has a positive association. Man is not a cat, so negative. They are human. They have gender. Man by itself does not necessarily designate royalty. A man is not a verb, and man is singular, not plural. And so you would put in these embeddings based on these relationships with each word, and that's how semantic meaning is spread so that the computer can understand it in its own language. Then the AI would basically run this through a series of neural networks. So if you had a complete sentence, the dog ate my homework, and you would look at the association of each word, in this case, how they associate with the other words. You would break the words up into 3 to 5 words, or however you decide to chunk it, and it creates that classification. And each of these create embeddings based on the association of all the other words with the other words. And that's at a high level explanation. And then the neural networks will run through those words and their embeddings through this process to bring out probabilities, or to define probabilities of that word being associated with another word. And those probabilities help the AI to actually understand how one word is related to another. What's the probability of that word being related to each other? And it's a very complex system. So once you run it through those neural networks, you'll see that there starts to be these little clusters of words that are associated with each other, and that you can add categories to. And so that's kind of how a neural network defines dimensional relationships at the highest dimensional level. Each word having its own vector, of course. Going back to the system, so we just completed the embedding process and talking about that. Those embeddings are then fed into an index so they can all be tracked, and the text chunks are also fed in. So these would be all associated with it in the metadata, and that text chunk, or the text embedding, the text chunk, and the actual metadata are then stored together in a vector database that can be accessed to retrieve new information. Again, that gets back to our retrieval concept. Now, we'll get to the last aspect, which is storing data. And you can see that if a human were to do this, there would be lots of very complicated mathematical aspects that you have to go through, calculating each level, which can be an extreme pain in the neck. So what we want to do is allow the computer to do that. The tool that we're using to store data is the Chroma database. And basically this system works both locally and in the cloud. So you can, if your company has a lot of private information it wants to preserve, it can use Chroma, which is a free application, and use it locally to store and retrieve data for a RAG system. It is connected very quickly with embedding models from Hugging Face, OpenAI, and Google, which makes it much easier to use. It's also included with many generation and indexing tools such as Langchain and Llama Index. It allows you to have a complete and full search. It does metadata filtering, so you never lose the sources, and it's compatible with multiple languages. So it's quite a nice system to use in this case. Now, let's talk about the actual retrieval augmented generation process and how it works. So you would have a query such as, what is a vector? And that query has to be embedded itself so that it can communicate with the embeddings in the data store. And your smart retriever actually conducts a semantic search, which is looking for words and associations and associations in meaning. In our case, we would break up the initial query and have the LLM generate a series of queries that could help enhance the search that you're looking for that particular answer. So it gives you a better answer through a series of questions rather than just one questions. Then it accesses the database and finds the documents that have the greatest similarity through a calculation using cosine similarity, which just basically tells you how closely associated a particular document is. And then it extracts each chunk with its assigned cosine similarity score and provides that new data to the chat box function. And the LLM consumes that information. It becomes part of its knowledge base, and then it provides a response based on the data that you have provided. And that's why it's called Retrieval Augmented Generation. The generated response is based on the new information rather than based on the data that it was trained on, which can help prevent and reduce hallucinations. And hallucinations are basically where an LLM will repeat something that is found somewhere within its database, or sometimes gives an answer that is not correct because it has some kind of slight word association with the question that was asked. And so all these processes will help reduce that. The Chroma database is quite easy to set up. So this is, well, there's always some great details that go into this, getting it perfectly, but the basic steps are that you provide it with the document. So in this case, the split documents, your embeddings have to be the same embeddings it's stored on have to be the same as the receiver or the smart retriever. And those, when the embeddings are the same, they can communicate with each other and find the words that are similar. So it stores that persistent data, and the retriever pulls that data out and gives it over to the LLM model. Now that brings us to the concept of the agentic aspect of RAG. And in this case, I used CrewAI. So I'm going to talk about CrewAI and what the advantages are. But basically, CrewAI is where you have a series of algorithms that use LLM models, so a series of chatbots, to act as agents. And each agent takes on a role, and the agents can work together and collaborate, or they can work independently. You can do it sequentially, parallel, hierarchical, depending on what you want to do. And the process that they extract information is usually based on a specific goal you give each agent, or that's the responsibility that you expect that agent to fulfill, all done through prompts. And then lastly, that you provided some tools. These can be external apps or tools that you actually can create. And you can actually assign a different large language model for an LLM for each agent. So agents could use different models to fact check each other. So let's look at how that would work with one agent. In a single agent, you would set up an agent who takes in a query, and the idea is that that particular agent would provide a response based on the parameters that you set. So the parameters for an agent are basically, you set a role, you define what the agent's going to do, you talk about what its goal is, you give it a little bit of a backstory to talk. So this helps enrich the interactions because these LLMs are working on prompts, and this is the role-playing aspect of an agent. And then again, you provided tools. You just set whether or not you want the response to be very short or long, and then you can also assign managers to manage the other agents. So that manager might have the sole responsibility of making sure each agent does its task or setting out a plan and so forth. The agents also have a series of algorithms that help them understand the task And so the tasks have the following parameters, which are description, which just talks about the steps you want that task to go through. So laying out very explicit directions can help a task or an agent come up with a response that fits more to what you were asking it to accomplish. Then you talk about what you expect that output to look like, and then you assign it the particular tools that it'll use. Those agents can work asynchronously, synchronously, and so that means that they work in parallel or they can work individually. And you can set a stage so that certain agents have to complete their task before another agent picks up that responsibility. And that's the context parameter, which basically says it has to receive from these previous agents the information before it actually completes it or even starts its job. So that's kind of how a singular agent would be set up. And I have some code right here just to show you how basic and straightforward it is, which is a great thing for people because they can understand the concept of how to set it up. But you just basically have your function for the particular agent, and you give that agent a name. Again, it's role, goal, backstory, and so forth. And then that agent also has a task. In this case, the tool is a search tool, which is defined as the SERPer dev tool, which Google made to help search the internet. And that particular agent will pull that task, and then a crew brings it all together. So that crew can include one agent or multiple agents telling you exactly how to lay this out. And the response that they provide can be either verbose or not. Again, if you want a short summary versus a full article, you can tell the agent to do that. Now, in the case of this particular presentation, the model that I'm going to show you uses multiple agents and thus agentic RAG, and this is the process that it goes through. So we'll basically have an internet searcher who uses the SERPer tool. We'll have news API, Reuters API, and these agents are responsible for extracting data that is similar or associated with the particular query. Then I have a UR manager who is dependent on the content from the internet searcher, and then pulls all the URLs that are not in the library yet, and puts them on a list, and then tells the scraper tool, which is Spider that we're using. The agent will be using the Spider scraper, and that agent actually goes and scrapes the website. It can scrape or crawl setting based on the parameters, and the only difference between scraping and crawling is that rather than scraping just one page, any website link on that page is then opened by the crawler, who then examines and extracts all the data from each of those steps. And then that data, that combined data, is then embedded and indexed and stored by the librarian agent. The librarian agent has the only responsibility they have is to pull all that data together and get it into a list, and then provide the human an output of what was chunked and what was stored. And that's what the librarian agent does. Then the news reporter gets that information from the librarian. The news reporter would ask the librarian for the data, and that news reporter would also use that advanced search tool to extract the data from the RAG library, and then writes an article. And then you could have another agent who fact checks that article to make sure it's accurate, that there weren't any problems in the data. That fact checker could also look for alternative viewpoints and add a paragraph that spells out specifically what the alternative viewpoint is for what was provided by the news report. Then an editor comes through and checks for hallucination and makes sure all the sourcing is correct. And that's the last step that comes together. And they make sure that the article that was provided fits and meets the category that was required in the steps. And so that's how an agentic RAG crew would work. Now, for the purposes of this briefing, this is the end of the PowerPoint, but I'm going to quickly just jump over to some code and show you what the actual code looks like. So these are the libraries that you would use. You have certain API keys that you would have to use to pull the data. And then you have the tool. So the collection tool, which scrapes or pulls the URLs. The spider scraper tool, which goes through and identifies and scrapes the data that needs to be extracted. This is the create vector tool, so you can see that there is chunking taking place using a recursive character splitter. And that data is chunked. Paths are created to where it's stored, and the specifics are given for the metadata that we want to store and retain. So IDs are provided and everything like that. And then the embedding tool is OpenAI, so it needs to be the same as the retriever tool. And then it's stored in the database, and then every cycle it goes through and verifies before storing a new document that that document hasn't been stored previously, and it keeps account of all the chunks that are stored into that database. And then finally, it just prints out a response. The vector store query is just basically the retriever, and it pulls out the similarity of documents based on the query that is submitted, and then make sure it provides the complete citation for that. So here's what these agents would look like. The SERPer agent is surfing the internet. A URL extracts the ones that are going to be recommended for scraping. The scraper agent scrapes it. The librarian stores it. The news writing agent would write that up, and then each of them have their own particular task with specific details given about what the expected thing. You can also output a file in this case. So, and then the crew executes everything and retains stuff in memory, caches the data, and the output. So for instance, here is the identified data from the searcher. What they did through here is they pulled the URL title and a snippet, and if a date was available, they pulled that, and they provided that information in a list. So I have it set to a limitation of 10 articles right now, and when we build the actual vector database, we'll extract a lot more data. The vector chunks, this just verifies how many chunks are being made from each article. So you can see that there's a lot of chunks in different articles. And then it writes a complete news article. And you can see here the way the steps that is been directed to take. The agent actually does an introduction and talks about what it's going to be discussed in the entire article. This is the new development that takes place. And then it's going to talk about why that new development came about and what the current impact of that new development is. And you can see that it is putting endnotes for each article, sourcing each article to the correct source. And then lastly, it talks about looking ahead into the future. This is like an outlook of what it expects to happen, and then its final concluding arguments. And so all the sources are put in there. So that is an example of how the Agentic RAG works. I thank you for your time, and I hope you enjoyed the presentation. And this concludes our discussion. Have a great day. Thank you.